It had inversion eigenvalues, minus, minus, plus, 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 plus. And so that whatever, x, okay? And we said that the Vanier centers of this phase at kx equals to 0 are where? So let's call this logarithm of the Wilson loop 1 over I. This is the Vanier centers, right? So where are they? At kx equals 0? Huh? Very good, thank you. And at kx equals to pi. And we wanted to look at the following flow. Okay? And then we said that if you add two bands to the system, so this was the flow, basically. Now you recognize that this flow is basically one Chern insulator with Chern number 1, right? And another Chern insulator with Chern number -1. So this flow is very similar to minus plus plus plus, which was the Chern insulator, plus another minus plus plus plus, but of opposite Chern numbers. And we're fine since inversion gives you that just the Chern number mod 2. Yeah? Remember that inversion by itself could not differentiate between Chern number 1 and -1, or 3, or 5. Yeah? Okay. So physically, this is just one Vanier center going in one direction, the other one going in the other direction. Or quantum hole for one branch with Chern number 1, quantum hole for another branch with Chern number -1, so +1, -1, which was pointed out by someone yesterday, is just the quantum spin Hall flow. But you don't have the symmetries of a quantum spin Hall state, which involves time reversal. I didn't even talk about time reversal here, and involves time reversal squared equals to -1. So you don't have those symmetries. So this is not the quantum spin Hall state. It has the same flow as a quantum spin Hall state for 2 bands, but it's fundamentally different for more bands. Why? Because then I added to this guy an s and a p orbital at the 1a Wyckoff position, which have these eigenvalues, or as was pointed out yesterday, an s and a p orbital at any Wyckoff position would add these eigenvalues. And what were the Vanier states for this pair of eigenvalues at kx equals 0? Sorry? Theta minus theta. And what were they here? Lambda minus lambda, because these were s and p orbitals, so they can sp hybridize in one direction, in the y direction, and stay sp hybridized. So what this means is that these orbitals are sp hybridized, which are s and p, because they have these inversion eigenvalues. They're sp hybridized in the y direction, and they stay sp hybridized in the y direction as I move momentum in the kx direction. Okay, that's what this means. Okay, and once I did that, then the following thing happens. I can do there's no symmetry at generic kx. There's no special symmetry at generic kx of the Vanier centers, because inversion sends Vanier centers and minus Vanier centers. So when two Vanier centers cross, they can actually split and anti-cross, as long as, of course, they split in an inversion symmetric way. Okay? So now I got from Wilson loop flow, which was this, to no Wilson loop flow, which is this. Yes, this is what we did last time. Yeah, remember? And this phase can be then written down. Okay? Yes. Sounds good. With a white. Okay, good. Let's do white. Okay. So we said that this equation, this plus this, which was Okay? Inversion symmetry makes me this be equal to this. Okay? This plus this equals to this, which has no Wilson loop winding. So Wilson loop winding plus, so I cannot describe this by maximally or by localized Wannier states because it winds. If I put unit cells, it winds. Plus no Wilson loop winding equals no Wilson loop winding. Yeah? Does it make sense? Okay. What, does it make sense?
So what did you do with the thing you are finding?
Sorry. Good. Okay. Good. Sorry. Okay. So this means that this state, which we call a state, call it state one. This is a two-band state. State one. Let's call it S state one, ST1. Plus what is this? This is an s orbital at position 1a. Plus a p orbital at position 1a. Okay? These are what these are. They're just atomic limits, elementary band representations at position 1a, or at any other position, actually, right? Remember, it was pointed out that I can put these at any other position and I'll still get the plus minus eigenvalues, as long as I put both s and p at the same position. Okay? And this one, I claim, this one has got the inversion eigenvalues. This full state has got inversion eigenvalues minus, minus, plus, minus, plus, minus, plus, minus, plus, 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 minus, plus, 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 minus, plus, 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 minus. Okay? And I claim that you can check, and I'm sure you've checked this yesterday, that this is the p orbital at 1c position plus p orbital at 1b position plus s orbital at 1a plus p orbital at 1d position. And I remind you the Wyckoff positions were in the lattice A, B, C, D, all with 1 because they have multiplicity 1. Okay? Yes? No? Okay. So this means that now I was able to make this phase not have Wannier flow. Okay? But there is still something that tells me that I can always make out of this. So this is a sum of atomic limits. Sum of atomic limits equals topological phase plus sum of atomic limits. That's counterintuitive. But I'm still able to tell you that somehow, if I just see these atomic limits on the right side, so if I don't know this, if I just see these atomic limits, I'm still able to tell you that these atomic limits could be made to be a topological state of two bands plus two trivial states. Okay, and the way I'm able to tell you is this double crossing here. So, the question is, for example, so the further question is, given just the right-hand side, so say you don't know about the left-hand side, right? Given just the right-hand side. The right-hand side is a combination of 4 atomic limits. I can add, a band at 1c, a p orbital at 1c, a p orbital at 1b, a p orbital at 1d, and a s orbital at 1a. Yeah? Is it clear that this means just... Okay. But now, so these are all atomic limits, but now I can do something in this projector, in this set of bands. I can switch around their eigenvalues so that they are no longer atomic band at 1a, atomic band at 1b, atomic band at 1c, at atomic band at 1d. I can switch their eigenvalues so that they are actually a topological state plus 2 different atomic limits. Okay? So the question is there something that tells me here that I can do this? For example, if I just had one band, S1A, and consider P1A. Okay? If I just had these 2 bands below the Fermi level, there would be nothing that would tell me that I can make out of these 2 bands something topological, okay, by switching them around. And there will be nothing that can tell me, because I cannot make anything topological out of these two bands by switching them around below the Fermi level. Okay? But out of these 4 bands, for example, out of these 4 bands, there is something that tells me that out of these 4 bands, I can create something topological plus something trivial out of 4 trivial bands. Does it make sense? Does the logic make sense? And what tells you are these double crossings here and here. So if I plotted the Wilson loop of these bands, I would get these double crossings. These are enforced by inversion. So if I plotted the Wilson loop of these 4 bands, it would look like this. Okay? But I would, or like some continuation of this, but I would have these double crossings.
Okay.
Yes?
But in order to know that we have this double crossing, we have to have knowledge about what you suggest us to look at, so to system 1 plus the other.
That's right. That's very good. That's right. But the point is, you can just not look at this system and look at the Wilson loop of these 4 bands. It will have this form. Of course, it might be a little bit squashed, etc., but it will have this form, because these are just enforced by inversion eigenvalues. So with this inversion eigenvalues, there's a one-to-one mapping between Wilson loop and inversion eigenvalues, and it will have this inversion eigenvalues and these Wilson loops. Is that clear? I know last night was a rough night for many of us, but is this clear? Okay. If it's not clear, ask questions right now. Yes?
So when you have these 4, these P1, C, P1, B, etc., how do you know when you connect them? What tells you? Because you can pick different ways to connect the Wilson loops, right? When you determine their values at 0 and pi.
Very good point. So if you know, so imagine I start from an atomic limit system. Then there's only really one way of connecting them. Okay? So first of all, do you agree with me that if you write the eigenvalues, so you just can write don't look at the left-hand side, just look at the right-hand side, and write their eigenvalues under inversion. Then you're going to know immediately by what we did in the first lecture and the second lecture that there's 2 eigenvalues here at pi, there's 1 eigenvalue here at some theta, and there's another one here. And here there's 2 at 0, and there's one at some lambda, and another one at some lambda. And really, in the atomic limit, when the system is to infinity, all these move to, when there's no hopping, all these move actually to where the atoms sit. But when you get hoppings, these come down, etc. These are forced to stay here. So now, there's not basically many options that you can do, because you know you have to have a crossing here. You know you have to have a crossing here. And you know that this is an atomic limit. So it cannot, Wilson loop cannot wind in the atomic limit. So you know the Wilson loop has to do this, because otherwise it would. So basically, you're kind of constrained by the symmetry and the fact that it's an atomic limit. But what I do know is that out of this atomic limit, out of these bands, I can let them be in the atomic limit, or I can make this phase. And I can make this phase by swapping around some eigenvalues. Does this make sense? Swapping around some eigenvalues internally in this projector. Is that clear, or should we go through that? So this phase has some eigenvalues, okay, under inversion, and they're these ones, okay? But they're ordered differently than in this phase. This phase has a band of 2 bands, a set of 2 bands sitting, close to each other, which have these 4 eigenvalues, plus another S1A band plus another P1A band. This phase has the same eigenvalues totally, but the bands are ordered differently. So I just have to swap some eigenvalues, and I get this topological phase, and I can form the projector in it, and I can see that the projector in this phase actually winds. Okay? Okay, let's get to C2 times T. So we go back to 1D, to our favorite problem. Wyckoff position 1A. So now, so the reason why I want to go to C2T is because that's the symmetry that, well, we're not going to get to graphene, but we're going to get to the phase that's in graphene. That's the symmetry that exists in graphene, and I'll tell you why. And the reason why we did this inversion symmetry thing is because the phase that you get from this symmetry is very similar to this phase, but a bit more complicated and more subtle. So let's just do it. So now I ditch inversion. So goal number 1 is going to be to get to a phase that's very similar to this, but subtle. And goal number 2 is to prove that this is the symmetry that exists in twisted bilayer graphene. Okay. So this is the 1A Wyckoff position, 1B, 1A, 1B, 1A, 1B, etc. Okay, in the unit cell, this is just this. Okay, if I pick this unit cell here, in fact, let me pick this origin here. And now I consider a system not with inversion symmetry. So, by the way, we can in one dimension for spinless groups, C2 is the same as inversion. Okay, yeah. But this we can consider spinless groups or spinful groups. In graphene, it's spinless. But that doesn't matter because, spin orbital coupling is small. But it doesn't matter. Once you have just C2T symmetry, this symmetry, if you don't have C2 and T separately, this symmetry is the same for spinless and spinful. Is that clear why? So spinless, C2 squares and T squares to what for spinless? For spinful, spinless. Spinful. For spinless, what do they do? C2 squares to what? T squares to what? Okay, but you don't have each of them. So if you have each of them separately, you can distinguish between spinful and spinless. But you don't have each of them separately. So you only have C2 times T. I'm only imposing C2 times T. It's a very, well, it's not a weak symmetry, but it's, it is what it is. What's C2 times T squared? 1 in both cases. Yeah? Is that clear? Okay. So we're not going to be restricted about what we're talking about, spinful or spinless, from now on. Okay? Now, because C2 times T is what operator? Is it unitary or anti-unitary? It's anti-unitary. Does it have eigenvalues? Anti-unitary operators do not have eigenvalues. I can multiply something. This is a complex conjugation. It's a unitary operator times complex conjugation. And depending on the phase that I put in here, if I take state 1, I can get to one value. If I take state I times 1, I get minus. Right? So this doesn't have eigenvalues, so this is very different from inversion. Difference 1. Difference 2, inversion maps K to minus K in the Briand zone. And we're only going to be talking about 1D and 2D Briand zones. So C2 times T maps what into what? K into? Huh? K into itself. Okay, so it's actually a symmetry now. So unlike inversion, so it's got one detriment to inversion, that it doesn't have eigenvalues at high symmetry points. Okay? Is that clear? But it's got something nicer than inversion, that it's actually local in K space. It takes K to K. Yeah? Clear? Okay. So now let's find out where the possible Wannier states can sit. Say I have one band in my system, one band system. Okay? Where can the Wannier states of, where can this, so atomic limit, atomic band, or adiabatically continuable to atomic band. Where does it have to sit? Where does center of charge have to sit if I have one band? 1A or? So you can sit at 1A or 1B. Okay, if it's a real representation, I don't need to double it, right? Because complex conjugation. Okay, so it can sit at 1A or 1B. So if it sits at 1A, what's the Wilson loop? What's the Wilson loop value in 1D? This is just a number. Huh? If it sits at 1B, what's the Wilson loop value? Very good. Okay. Notice that I cannot now describe my states as SMP orbitals. Okay? Because this is an anti-unitary operator. It doesn't have eigenvalues. Okay? There's no more distinction between the SMP orbitals. Yes.
Is C2T the only symmetry you have?
Yes. C2T is the only symmetry. So I choose to have this. In graphene, you have some C3, you have some C2X, but this is actually the symmetry that protects what I'm going to be talking about. So it's the only symmetry you have. So it takes C2T takes this to this, and it acts with complex conjugation on it. Very good. So you don't have anymore this eigenvalue, nice eigenvalue structure that I had with inversion. So that means that what's gone? SP hybridization is gone. Okay? So I cannot describe things by S or P orbitals. SP hybridization is gone. So let's find out the structure of the bands. If I have a two-band system, where can they sit? Where can these two centers of charge sit generically? Anywhere, exactly. So they can sit somewhere here and somewhere here, as long as this is the C2 of this plus time reversal. Or they can sit here and here. They can sit anywhere. Okay? Is that clear? Unlike in the inversion symmetric system, where if I had two s orbitals at 1a, they couldn't move away from 1a because they would need to move away through sp hybridization. Remember, if I had two s orbitals at 1a, then their Wilson loop eigenvalues were 0, 0. They couldn't move away because that would imply sp hybridization. I had just had two s orbitals at 1a with inversion. Yeah? I need to have sp orbitals here to move away. Here, if I have with C2 times T, if I have two bands, everything can move away. Yeah? Does that make sense? Okay, so what are the Wilson eigenvalues for these? Theta minus theta. Very good. You can clearly see them. And the minus theta comes because of the C2. Okay, three-band system. What are the Wilson loop eigenvalues? Let's just not go through examples. What are the Wilson loop possible Wilson generically for the three-band system? There are two types. There could be two types. Theta minus theta and 0, or theta minus theta and pi. Yeah? Because I have an odd number of bands. Two of them I would have to put at theta at minus theta, but the third one I'd be locked to either put it here or here by C2 times T. Yeah? Okay. Very good. So that means that these are the phases. Now very interesting in one dimension. Now we're going to go to 2 dimensions where things become very interesting. And it's pretty clear. If I have 4-band systems, I can get theta minus theta, lambda minus lambda. There's this alternation, right? And you see, even though there's no eigenvalue, the C2T, you don't have eigenvalues, it's an anti-unitary operator, you still have some Wilson loops for odd band system being stuck to some exact value, theta or pi. Okay. So now we're going to go to 2 dimensions. And look at the C to T invariant system in 2 dimensions. Again, what are the maximal Wyckoff positions? Well, what are they? They're the same as before, just that I cannot describe my states by eigenvalues because I have a K, a complex conjugation operator. It's an anti-unitary operator. It does not have eigenvalues. Okay? So now, what I want to do is I want to create a band that has a Wilson loop that looks very much like this. Okay? So question, can we create a 2-band system, 2 occupied bands, whose Wilson loop winds? Okay? So what do you think? Can we or can we not? Well, I mean, if not, then we get an early break. but so the answer is yes, we can. But there's a twist. Where were these crossings in the case of inversion? So this is the Wilson loop spectrum, this is Kx. Where were these crossings? At Kx 0 and pi. And this was Wilson loop pi, 0 minus pi. Okay? And these were enforced by inversion symmetry. But we now just said right here that in 1D with C2 times T, for 2 bands, I can have theta minus theta. Right? So that means that naively, for inversion for C2 times T, here I have pi, I have 2 bands, pi pi, okay? But generically I said there's theta minus theta. So generically I would say that I could do this, I could put it here. Yeah? I could, at 0, I could just split them up, because I just said I don't have this inversion eigenvalues that fixes my Vanier centers to be at pi there. And I can move them to theta minus theta. Same thing here, yeah? I can move them to lambda minus lambda from here to here. And now I'm a bit screwed. Okay? So moral of the story, this process cannot happen. Okay? And there's a reason why it cannot happen, and we're going to find it now. What can happen, however, how do you distinguish? So I've told you that. So I've lied to you somewhere. I've told you that this process can happen theta minus theta. Okay? Then I've said that I can form a stable Wilson loop that looks like this with stable crossing. But that runs into ground with this logic because I can move the eigenvalues if they're doubled here. That just means I have two bands. And I can move the eigenvalues to theta minus theta. So I should be able to do this. Okay? But there's a twist. The twist is that you can always do this locally in K-space, but not globally. So this is basically 1D Val nodes. So in 1D we don't have Val nodes in one dimension in the real band structures, but in the Vanier center structure you do. So this is 1D Val nodes in the Vanier Hamiltonian. So let me give you the punchline of what happens first, and then tell you why. So locally at every k, by changing parameters, I can transform a pi pi into a theta minus theta, just like I said there. Okay? At every kx. So by changing parameters, I can transform this into this. Let me just redo it. So this is wrong. This cannot happen. But what can happen is that, with inversion symmetry, of course, kx equals 0 and pi are special. But with C2t, kx equals 0 and pi are not special at all. Right? Is that clear? C2t this leaves k invariant, so k equals 0 and pi are not special with C2 times time reversal. So what happens is that since I have two bands, at any k, I can make these two bands. So for example, if they were degenerate here with inversion, with C2 times t, I can make them like this. So I can do what I said here. Okay? And here, I can make them like this. But what will happen is that all I have done is to move this crossing point somewhere further. So I've done this. So okay? So that's how you mix, how you have both of the things I said right. So you can have this type of flow. It's just that these crossings in the flow, which make the system not Vanierizable, the system of two bands, not being able to be expressed by localized orbitals because the Wilson loop flows, the Vanier center flow. These crossings do not need to sit at high symmetry points because there aren't any high symmetry points with this symmetry. So what happens is I can always move these up or down here just by changing parameters. Just like I said, I can move two bands. With two bands, my Vanier states can have eigenvalues theta minus theta. I can move them here, but I cannot get rid of this crossing. I'll have moved this crossing further away. Okay? Likewise, by changing further the parameters of the Hamiltonian, I can move this crossing here and this crossing somewhere here. Okay? And I can move them everywhere. Okay? I can just get all the parameters. But the point is this winding here can never be broken. Yes?
So you're talking about the crossings on the top and the bottom?
I'm only talking about the crossings at very good. I'm only talking about crossings at Wilson eigenvalue pi and 0. Those are the only ones that are protected. Why? Because C2 times t takes what eigenvalues into what eigenvalues. C2 times t takes Wilson loop eigenvalues theta into minus theta. So if I had a crossing here, there would be no symmetry that it would take Wilson loop eigenvalues here. But if there are theta here, then the Wilson loop, the symmetry actually acts around, well, acts on this crossing and leaves it invariant. Whereas if I had a crossing here, if I had another band here, then this moves, C2 times t moves it here. Okay? So that's why, and that's why this phase is very similar to the one before. It's fragile if I add two more bands. Yes? And then you.
On it says that you need to have the pi and a 0. Can you also avoid this altogether?
You can avoid this altogether with C2 times t, you're right. you can avoid, you can have this. You can certainly have this. This is allowed. But the point is these are distinct classes. This is so with C2 times time reversal, there's distinct classes of topological phases, and this is a distinct class from this. Very good, yes. Just like with inversion, you could have had this too, but it's a distinct topological class from that. And we're going to find out how many topological classes there are with C2 times time reversal. And graphene realizes twisted bilayer graphene realizes exactly this one, the simplest one. Well, the simplest one. Actually, it's got a lot of stability. Yes, sorry, there was one, and then there was, yes.
Okay, so that other crossing just near the high points.
Which one? This one?
No, the one in the middle.
This one.
Yeah.
This is around Vanya center 0, kx equals to pi.
Yes. That crossing is also protected by symmetry.
Yes, yes. You see, they both have to be protected in order for the Wilson loop to wind. If this wasn't protected and this was protected, the Wilson loop wouldn't wind. It would open a gap and it would do this, right? So for a Wilson loop to wind, it would need to be protected, and we're going to understand why they're protected, but we need to dig a bit deeper. But if this is protected and this is protected, they can move around. They're like Val points in one dimension, right? A Val point is like in 3 dimensions that, you've heard a lot about in the last talks, right? They can move around. They're not enforced by symmetry. You can have Val points without any symmetry. They can move around, but you cannot get rid of them. This is the same thing in 1 dimension. The only way I can get rid of this guy is if I have another Val point on this line. This is a Val point in the Vanya Hamiltonian. Okay. Sorry, yes, there was another question. It's this.
My question was why exactly you are protected, but I guess you will.
Yes, we're going there now. Yes. Any more questions? Yes.
Why it's some other symmetry which doesn't really
If you add more symmetry, no. So if C2T is a symmetry of the Hamiltonian, then if you have this, it's stuck to be this. If you add another symmetry that doesn't commute with C2T, what that symmetry will do is it'll probably flip some bands. Okay. So moral of the story: either you can build a 2-band model. Might not be able to build a 2-band model with that symmetry. You might need more bands. But either you can build a 2-band model, and then if it's got this symmetry, C2T, you can add whatever you want to it, and it'll stay the same, or you can't build it. Yes?
You said that the Wilson loop at 0 crossing is protected.
And at pi.
Yeah, but before, what we had at 0, Wilson 0, we had 2 crossings, right? We had
No, you had 1 crossing. Yet here, there was a crossing at k equals pi. Right? There's 2 states here, and this k equals minus pi is the same point. It's just 1 crossing. There are 2 levels. Same thing as here. 1 crossing, 2 levels. Right? Which one?
In the vertical, the crossings are individual.
There's 1 crossing here. 1 crossing here. Agreed? There's 1 crossing here. 1 crossing here. Agreed? Okay, good. It's just that the crossing doesn't need to get to stay at the high symmetry point. Okay? Any more questions? Yes.
The distance between the crossings can also shrink.
Yes, it can shrink freely, but as you know, Wilson loops are basically continuous. So you cannot have like a if you have a accumulation point, that means that you're making the system gapless, and that's the only way that it can shrink continuously, but this can never annihilate because they're different. Very good. Any more questions? Okay, so let's just see how we prove this. Well, the way we prove this is, well, not simple, but we're just going to prove it. So the Wilson loop, remember what I think Titus told you, is a unitary operator, right? Did he mention this? Okay. So any unitary operator, I can write it down as E2 some Hermitian operator. And this is the Wilson loop as a function of kx for this system. And this is, you can call it the Vanier Hamiltonian. But the way you should think of it is it's the Hermitian operator whose eigenvalues, mod 2 pi, are what? The Vanier centers. So in particular, right, the eigenvalues of this operator, mod 2 pi, are just the Vanier centers. This is what I was plotting by log, okay? And since the eigenvalues are the Vanier centers, obviously this regulates splitting between Vanier centers, this Hamiltonian. Yeah? Is it clear that since the eigenvalues of this Hamiltonian are the Vanier centers, splitting between Vanier centers or symmetries of Vanier centers are described by this Hamiltonian? Yeah? Okay. So we're just going to find out what this Hamiltonian is for two bands, and this is important. Okay, so let's find it. So we're going to apply the symmetry. The only thing that we have to apply is the symmetry. And the symmetry that I'm going to choose for C2T to make it easy is just complex conjugation. So I take the unitary part to be 1. I can pick that gauge, but you can take whatever you want to. It'll still be fine. Okay? Yes? Now, normally, right, this was my Briand zone, Kx, Ky, right? I took my Wilson loop in the y direction. Yeah? What does C2T does to the contour of the Wilson loop, right? So the Wilson loop involved taking projectors, discretizing this, what Titus showed you, taking in this direction. What does C2T do? Well, if it was just time reversal will move it to minus k and will reverse the contour. Reversing the contour, you'd get a dagger in the Wilson loop. But C2T moves it back. Yeah? So you don't get a dagger anymore. C2T leaves the contour invariant. Okay? So the only symmetry of the Wilson loop is that since I have the C2T symmetry and leaves the contour invariant, complex conjugation times the Wilson loop at Kx times complex conjugation is equal to the Wilson loop at Kx. You can obtain this easily from what Titus showed you, from the fact that the Wilson loop is the projector here times the projector here times the projector here times the projector here times the projector here, blah, blah, blah. Each of these projectors satisfies this equation. Okay? So the Wilson loop satisfies it. Is this clear? Now, is it clear that this means that h omega of kx minus star is equal to h omega of kx? Or omega w. Dyslexia. Is it clear that this... So this is the imposing C2k on the Wilson loop, because the Wilson loop is made out of projectors of the Hamiltonian, which are invariant under C2k. The Wilson loop is projector here times the projector here times blah, 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 up to here. You discretize this at every kx. These projectors satisfy this equation. Okay? So the Wilson loop satisfies this equation. And it's just complex conjugation, so this just gives this a star. Yeah? So is this clear? So now we're gonna see what this implies. So what does this imply? Well, first of all, you can see that C2T acts as particle Hall at every k on the Vanier center Hamiltonian. Okay? It's kx. So doing my Wilson loop as a function of kx, sorry, all of these are kx. Doing my Wilson loop as a function of kx, and my Wilson loop is taken in the y direction. So the way you construct your Wilson loop is take the projector at this kx, at this ky, times the projector at this kx, at this ky, blah, 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 blah. Each of these projectors satisfies this, so their product will satisfy this. And that's the Wilson loop satisfying this. Very good. More questions? Because time reversal reverses the contour, but C2 flips it back. Yeah? Time reversal does this, C2 does this. Is that clear? Okay. So now what we're going to ask is, let me assume I have two bands, two occupied bands, so two bands in the Wilson loop, right? How can I expand the Hermitian operator into two bands? So I have two bands, so this is generic for any number of bands with C2 times time reversal. I can write the Wilson loop as e to the I h Vanya, and h Vanya has to satisfy this equation for any number of bands. Okay? But the fundamental constraint appears when you have two bands. Okay? So how do I write a Hermitian Hamiltonian? So this is Hermitian. It's not necessarily local, but I don't care. But how do I write, how do I expand the Hermitian operator of two bands? This by is some d k x dot sigma, as was shown in the Andreas' lectures. Okay, yeah? Plus some epsilon times identity, epsilon of kx. Yeah? And now we're going to impose this symmetry on this operator. So let's impose it. So minus dx of k sigma x plus dy of k sigma y. This k is kx, I'm not rewriting it. Minus dz of k sigma z minus epsilon of k identity. This has to be equal to dx of k sigma x plus dy of k sigma y minus dz of k sigma z minus epsilon of k times identity. Is that clear? Sorry, dyslexia again, thank you. I was just keeping you guys in check. Is this, yeah? Is the only thing that flips back, so everything gets a minus on the left-hand side, but the sigma y matrix, which has a star. You can check that a similar thing happens in every gauge. I can take here sigma z, whatever it is. The same is, I'm just picking a gauge, but the same thing happens in every gauge. I picked a gauge by generically some unitary here. Okay? So what does this mean? It means that dx of k is equal to what? dz of k is equal to what? d epsilon of k is equal to what? This is, by the way, mod pi or 2 pi. Okay, they're mod pi. They can be mod pi. Okay, because for pi, this is an equation mod pi. But let's just focus around some crossing here. Okay, so the Hamiltonian, so up to mod pi, so up to mod pi's, the Hamiltonian, the Vanya Hamiltonian, is dy of k sigma y. Up to mod pi's that are not extremely important for now, for making this point. Is this clear? This is a 1D Weyl system. So, moral of the story, if this has a crossing, which means dy of k proportional to k, either k or k plus pi. Okay, so if I have a crossing around 0, it will be proportional to k. Yeah? If I had a crossing around pi, it would be proportional to pi. Let's leave the crossing around 0. Obviously, by a redefinition of the unit cell, I can move this to here, right? So if this is stable, this is going to be stable. So let's just assume, so, how do you find out if this is a stable, this is a valve system in one dimension. So valve systems basically, as was shown, you can move the valve point around, but you can never get rid of it, right? So let's assume, so what you do to prove the stability of valve points, you assume you have a crossing, and then you try to move it around. So let's assume I have a crossing. So if I have a crossing, then HW is K sigma Y. This is a crossing. And now let me try to move it around. Or let me try to gap it. Sorry, not moving around. Let's try to gap it. Well, the only term I can add is M sigma Y, right? Because the Hamiltonian has to be of this form. So if I add M sigma Y, have I gapped it? Well, I've gapped it at K equals 0, just like I said there. But what have I done with it? I moved it at K equals minus M. Okay? More of the story is if you have a crossing at some point, you can move it around but not get rid of it. You need another crossing, okay, to get rid of it. Questions about this? Come on. Yes. There's no Chern number for this. Chern number is 0. You can notice here, right? However, in some gauge, you're onto something. In some gauge, well, in this gauge, the winding is just the winding of this this one parameter over the kx. Okay, so in this gauge, but in more complicated gauges, this is a bit, this rotates between all these matrices. But the moral of the story is there's always just one matrix that couples to a crossing, and then you can only move this crossing. Just like in the valve system. The valve system was 3 Pauli matrices, 3 dimensions, 3 Ks. So you could never gap it on any K. This is 1 Pauli matrix, 1 K. Yeah? But of course you need the symmetry for this because there's no valves in 1 dimension. Okay, more questions? More questions? Yes. Yeah, so Nielsen-Yoemiya works the same. You need 2 of these to gap. Okay? You have a Nielsen-Yoemiya with, of course, with the symmetry, and it works the same. You need 2 of these to gap. You cannot gap 1, right? You just move it around. That's why if I just have 1 here, I just move it around. This one can never gap because this one cannot touch this one. They're stuck here. Okay? Notice that if it's at 0, they're stuck at 0. And of course, locally, I can move them. I can move it at K. I can even make this crossing go further. I can do this crossing like this. Okay? But I cannot kill this crossing. And also, the eigenvalues have to come in pairs. Okay, so for every theta, you have a minus theta. The star is a Hermitian operator. The eigenvalues of this guy are real. The star doesn't count for the eigenvalues. So for the eigenvalue of theta, you have an eigenvalue of minus theta. Okay, and these crossings are stable. So if you have 1 crossing here and 1 crossing here, you can never get rid of them. Okay, very good. More questions while I erase this. More questions? Come on. No? Yeah, that's right. Well, no, you can, that will require more work. That's specific for her Hamiltonian, right? You can have this, you can certainly have, this topological phase happens in bilayer graphene, twisted bilayer graphene, with exactly this winding. Okay, so I can tell you that you can have it. It's an allowed phase, right? Since I haven't written down any Hamiltonian, I'm not telling you where you're going to have it, but you can take the graphene Hamiltonian, that's where you have it. Does that make sense? Okay. Yes?
You have the same flow as
Well, you see, this is the problem with seeing things on the edges is that C2T does not, the edge breaks the C2T symmetry. Right? So actually there's no edge states in this topological phase, but there are corner states of the higher order type. Well, the way you interpret the spectral flow is that you can never write, for example, so if I have just these two bands in a system, there's no way I can write a tight binding model for them. Okay? For just these two bands. These two bands have to be part of a larger system with the same spectral flow for the other bands. Because the total, you can only write tight binding models for a set of bands for which the Wilson projector doesn't flow. Why? Because tight binding models are exactly Wannier models, right? So, for example, it immediately tells you that all the searches, so the searches in graphene for a tight binding model of the twisted bilayer graphene for a tight binding model only of the lowest two bands are futile. They can never work, right? Second of all, it also tells you that you have some extended states in the system, right? So the Wannier state flow means you can never localize all the states. So it will tell you that you have some extended states in the system. And in twisted bilayer graphene, this is a flat band with some extended states. So, so it tells you that basically it's the interacting physics is probably very different. I don't know what it is, but it tells you there's many differences between, having a model that just has, that you can describe in terms of localized Wannier orbitals means you can localize all the electrons. Here, I will never be able to localize all the electrons unless I go through some phase transition and have some nice interacting state, whatever. So yeah. More questions? 5 minutes, good. More questions? Okay, so now let me show you that this is, let me show you another state. Okay? This is another Wilson loop flow in a C2T system. Okay? And what's the winding here? Well, you got winding in positive direction and winding in negative direction. But what is it? 2, okay, or -2, depending how you count it. Okay? So now, you can clearly see that there's a Z classification of these systems with C2T, because I can make Z windings, yeah? And that Z classification stems from the fact that this operator imposes a reality condition on the actual Hamiltonian. So K times the Hamiltonian times K, this is the actual Hamiltonian, is equal to the Hamiltonian. So it makes this basically an orthogonal matrix. And pi 2, because we're in 2 dimensions, 2-dimension torus, pi 2 of pi 2 of O2 is equal to Z. So O2 is the subspace of occupied bands, of 2 occupied bands, okay? Pi 2, I'm in 2 dimensions. I compute a second homotopy group of, this is on the Hamiltonian, and this is Z. And this Z is just nothing else but the winding of the Wilson loop. Now, if I add more bands to the system, I have the following property that pi 2 of ON, n number of bands, is, anybody knows? Is Z2. Okay? These are just, Wikipedia them. So this means that I should expect something weird to happen if I add more bands. The classification will go from Z, which is just this winding 0, 1, 2, I can wind more, 3, that's just this Z, for 2 bands. If I add more bands, the classification should become Z2. Okay, so let's see it. Let's just add more bands. We just do the same as we did, so we add trivial bands with no winding, the same as we did in the inversion case. So I'm adding this band. What do I need to do if I add one band here? Huh? Yeah, but that's right. But I need to add this. If the band is not at 0 or pi, I need to add another one. So if I add two bands, what will happen? So say it again, sorry, please. Gap, 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 gap. Is this clear? So this is very similar to the inversion case. Yeah? Okay. Let me add the same two bands here. So now I've added bands to the system. So this is the same as the inversion case, just with a different symmetry and with a different mechanism. So let me add bands here. What do these do? I added two bands to this state. So this is another state of winding number 2. Okay? Is it clear that it becomes like this? Still broken Wilson flow, but how can I distinguish this from this? Well, what I can do here is I have two vials, right? This guy here looks like this, okay? I could have this around pi, yeah? This, you can continue it here. You can take this down and put it here, yeah? And I can just pull these bands apart by some more, without doing, I can just pull these bands apart, and I can kill this vial with this vial. Yeah? So this guy can have no crossing on this axis. So once I pull these apart, these will look like this. So I can pull these apart like this, and I can pull these apart, and I can make this system look like this. 4 bands. Is it clear?
That's just an accident.
Well, these are not accidental. They're vials, right? All of these are vials, okay, in 1D. But in this case, I have 2 of them. So I can take one and kill it with the other, just like I can take 2 vials and annihilate them. But in this case, I have 1. I remain with 1. Even after I add the bands. So in this case, I can never get rid of this guy. Yeah? Sorry? Right, so of course, if you add, you can always add to a topological insulator another topological insulator. And then you get to, so if I add it to a band with winding 1, another band with winding 1, I get a band of winding 2, for example. But in this case, the question was, I have this 2-band system, which is a Z classification. And I add more bands, and now the classification collapsed to Z2. And the Z2 is just the parity of the crossings here. Okay? And this is actually related to corner states in graphene, twisted bilayer graphene. Okay, so that's it. Thank you. Yes, there you go.
So before, with these crossings that you leave, right, they were protected, say, the crossings that have in the middle. But now you say you have to put it apart.
Right, very good. So let's draw it before. They were protected because the one at 0 was followed by one at pi. Okay, so they were protected because of this.
I see.
Make sense?
Yeah, I see.
Okay, so they're protected because the one at 0 is followed by one at pi. It's followed by one at 0. Right? So that's why I couldn't mix these two, because mixing these two would mean bringing this down from pi to 0, which I cannot do. But once I've broken the flow, I can certainly do that. Now, very good question. Yeah. More questions?
So there is this physical manifestation in the corner more, you're saying, but also like similarly, I guess, to this inversion case in the previous lecture. Is it non-trivial in the sense of linear localizability? No, right? So you
No, these are Vanier localized.
all linear localized.
Yeah, once you add more bands.
Right.
This is not Vanier localized.
Right.
This is Vanier localized, but there's a remnant. You still know that there's something non-trivial.
And non-trivial here with the physical manifestation.
Well, for example, the physical manifestation will be corner. I don't have the time to go through it, but yeah, the physical and this index you can compute it,
Right.
even for forever. Yeah, Stiefner-Whitney index. Yeah.
I'm afraid that should be the last question, and then we should bother Andrei over the lunch break, because otherwise we don't get to next week. It's too late for everything. So yeah, one last question.
Okay, so in the previous lecture you said that all known qualities will somehow be related to the quality of these Wilson loops. Is that saying that all the quality can be described by these crossings at 0 and 5 of these Wilson loops?
For C2T, for the C2T case, yes.
And in other cases there might be other protected.
In other cases you have to implement the symmetry of the group on the Wilson loops. You have to look at the protected crossings, if they're protected by eigenvalues, or if they're protected by not by eigenvalues but by some weird Weyl-like physics, like here. You have to look at what the Vanier centers do, and it's not always obvious. But so far, there hasn't been the case that there's a Vanier there's a Vanier center property that is not describable by the Wilson loops. But by that, I don't mean just the Wilson. You can do more complicated things. So, for example, you can get this crossing here. You can determine this crossing by just the determinant of this Wilson of Wilson. And so you can get. You might need to dig deeper in the Wilson loop. But so far is.
There's a crossing, I know that I cannot construct localized one-way functions.
Well, if there's a winding,
That's
here you can. Right? There's no winding here anymore. The Wilson, yeah. But even though you cannot, even though you can construct maximally localized Vanier states here, there's still a stable index that remains, which is this Z2, which you can compute and differentiate phases by.